Okay, I want to go over a few homework questions from chapter 7, all right, and look at how we apply the principles of momentum, and we'll also end up going to apply the principles of energy from the previous chapter. Okay, so in this one, we have a basketball, okay, drop from rest, the initial 0, and right before it hits the floor, they give you the momentum in magnitude, okay? So what I did is I chose this coordinate system, so downwards positive, so my momentum when it hits the ground is positive 3.3. And they want to know what's that height that it was dropped from, okay? Well, if I write momentum as mv, there's no height h in mv. So that means I have to use energy. So here's our energy expression, okay? The only way the energy can change is if I have non-conservative forces doing work, and the only thing that acts on the ball as it falls is gravity, so there are no non-conservative forces that act. So initial energy is equal to final energy. So I chose my reference point for potential energy right there. So E initial is K initial plus potential initial, and same for final. So in my picture, K initial is 0, that's 0. Initial potential energy is mgh. Okay. Final potential energy when it hits the ground is 1/2 mv final squared, and final potential energy at the ground is 0. So I can solve this for h, and that's what I want. But I don't know v final when it hits the ground. But they give me the momentum when it hits the ground. They tell me the momentum is 3.3. So just solve this for v final, which I did. Okay. They give the momentum, that's 3.3 in the correct units. They give you the mass, and that gives you a number for v final, and then you put it right back in there, and that gives you the height. Okay, so that was using energy, the old chapter, and momentum. Okay, all right. And again, the reason why we can't conserve momentum, okay, remember here's Newton's second law for momentum, okay, that is there a net external force on the ball? Yeah, you have mg, points downward. So since there's a net external force, okay, the momentum can change. Momentum's not conserved. Okay, so P initial is not equal to P final. Initial momentum 0, final momentum is 3.3. Okay, so initially momentum 0, final momentum is not. Okay, why is that? That's because you had this gravitational force that sped it up. Okay, question 5. This is similar to the problem we did in the notes, right? 2 cars compressed with a spring, okay? And then I had a rope between them, the rope broke, and these things sprung apart. So this is just now 2 people. So here's my before picture, okay? I called one person E and one person B, okay, named after their names, okay? So before picture, they're standing there. The after picture, they push off, and one's moving to the left and one's moving to the right. So exact same as that problem, okay? All right, so they give you the velocity that that person goes off at. They give you the velocity that person goes off at, okay? And I'm writing that one as plus, that one's minus, right? So I'm just using a regular coordinate system. And they want you to find the ratio of the masses. So I'm going to conserve momentum for the system. Okay, so P initial equals P final. Initial momentum is 0. Okay, they're not moving. That's 0. And I have P final for E and P final for B. Okay, and then for momentum, remember momentum is mv. So for person E, I put in their mass times their final velocity. For B, I put in their mass times their final velocity. Okay, and then I brought this one over. So I have mass of B, V final B, right there, equal to minus that stuff. I brought it over. Okay, and I'm trying to find that ratio. So I just took this mass of E, I divided both sides by that. So there's my ratio, and then this velocity winds up on the bottom right there. Okay, so I know my V final for person E, okay, that was given to the left, so that's why it's a negative, and then I get the ratio of those two masses. Okay, so this question is 2 parts. So basically I have someone standing on the ground watching a lumberjack on a log. Okay, so we're watching them. So they start here at rest. Lumberjack is on the left side of the log. So they're M1, log is M2. Nothing's moving. Okay, that's my before picture. Okay, then the lumberjack starts to run. Okay, and right when they get to the end, they tell me the lumberjack is going 3.8 meters per second as measured from that person on the shore, on the ground. So this is my after picture. That's after. Okay, so here's the lumberjack at the end, okay, with that speed. And they want you to find in part A, what is the velocity of the log? So in the before picture, you have no motion. Now the lumberjack's moving to the right. Okay, so if you start with no momentum or no motion, and now in the final picture you have something that moves to the right, there better be something that moves to the left, and that's the log. And that's just like the balloon, and that's just like the rocket or the astronaut in the jetpack. Okay, if something is at rest and now something of that system starts to move to the right, that means something has to move to the left, or if something is ejected to the left, something has to move to the right to conserve that concept of motion. Okay, so I want to find the final speed of the log. Okay, so I went up here. So I conserve momentum for the system. So initial momentum is 0, okay, because this picture, nothing's moving. And final momentum is P1 final for the person plus P2 final for the log. Okay, so I wrote MV for each and then solved it for V2 final. I put in my values, and it turned out to be a negative number, which makes sense because I know the log is headed to the left. So when they ask for what's the velocity, make sure you put in the minus sign. Okay. Part B, gotta be careful. Okay, so in part A, the lumberjack was right there. Okay, that was for part A. For part B, now the lumberjack jumps off of the first log and is going to land on the other log, which I called M3. Okay, so for part B, there's my before picture. So the lumberjack has just left the first log, okay, at that speed. My after picture, now he lands on that log and they both move off to the right. And they want to find what's the speed of that log. So I conserve momentum for the system for part B. So initial momentum is I have P2 initial, that's the lumberjack, plus P3 initial, that's the log, is P final, which is the combination. So for the lumberjack, there's the momentum for the lumberjack. For the log, initial picture of the log, that's not moving. So its momentum is 0. And then the final picture, the lumberjack is on the log. So for the mass, they're stuck together. And then you have everything in here except for V final. And that comes out to be a positive number. That means the lumberjack and log are going to be moving off to the right. Okay, so part B would be no different than if you ran and then jumped on a skateboard. You and the skateboard would now be moving in that direction. Okay, so question 8's a little bit messy. Okay, so question 8, again, is kind of similar to these two carts attached to a spring, and then the spring broke off and both carts went in their own direction. Okay, here I have two people hanging from a rope. Okay, and they push off. Okay, they push off from each other, which now looks like that. So one person moves to the left, one person moves to the right. Okay, what makes this different is now person number 1 goes up to some height h, little h. Person number 2 goes up to some height big H. Okay, and they're asking you to find to what height does person Ed rise up to. So they're asking for capital H. What is that height? Okay, well, there is no H's in momentum. P initial equals P final. So that's an energy problem. Okay, so if I want to find the height that person number 2, that's what I called Ed, person number 2. Okay, if I want to find that height, I use our energy expression. Okay, and it's from right after they push off. So I have that speed that I have to find. Okay, their push off speed, and they come up here to the top where they're at rest. So the energy down here is all kinetic. Energy up here is all potential. So here's our energy expression. Okay, are there any non-conservative forces that act? Yeah, the string does. But we showed that the string tension is always perpendicular to the direction it's going, because the string tension's along the radius, okay, and they're moving tangentially. Okay, so the angle between them is 90 degrees, so the string tension does no work. So that's 0. So energy is conserved. So after they've pushed apart, then I'm conserving energy. So for person number 2, E initial goes E final. I put my reference point for potential energy at the height of the people. So initial energy, I wrote potential, kinetic, then final potential and kinetic. Initial potential is my reference point, that's 0. Initial kinetic, I wrote number 2. Final potential is up here, PE final. So it's MGH or M2GH. Final kinetic, remember, this is how high they go. So they're stopped up here. So K equals 0 up at the top. Okay. All right, and then I can solve this for H. I can get rid of the masses. Okay, that's what they want. But I don't know the speed with which this person pushes off. Okay, I'm trying to find that push apart speed. All right. So to find that speed, I have to conserve momentum for the initial push apart, kind of like this up here, for the initial push apart event. So I conserve momentum, and if I'm conserving momentum, okay, that's now my before picture, and this, maybe I'll make it in yellow, which is hard to see, okay, that's my after event, right after they push apart. Okay, so you can think of this as before, and that'd be after. And now instead of they're carts, they're just people attached with a string. So initial momentum 0, and then I have P1 final plus P2 final. Okay, so P1 final is M1 V1 final. P2 final is M2 V2 final. Okay, I'm trying to find V2 final. Okay, I know I kind of swap notation. That's okay. Here I have V final for person 2. Here I have V2 final. Okay, so I didn't mean to swap the notation, but as long as you can understand which one it is, that's fine. Okay, so it really should be V2 and then a final, or V2 and then initial. Okay, so that's good. All right, so I can solve this for V2 final. Okay, so I just solve this whole thing for V2 final, right? But I don't know V1, all right? I don't know V1 final, the speed with which this person left after being pushed off. Well, I do conservation of energy, same thing I did before for person number 1. Okay, so I conserve energy for person number 1. Okay, that's from here to there. Okay, so initial energy for person 1 is all kinetic. Final energy at the top, okay, the top for person number 1, all potential. So initial kinetic is equal to final kinetic. Okay, remember I'm using little h because we're up here. Okay, get rid of the m's, and then I solve that for V1 final, and I get that as a number. That goes into there. So now I get V2 final. That's a number. And then I take that and I put that right, whoops, that's okay. I stick it right there, and then that gives me my height h that I'm trying to find. Okay, so this one is a little more involved in the sense that you have two things colliding. Bullet hits a block, bullet embeds itself in the block, and they both keep moving, and they want you to calculate the percentage of the bullet's initial kinetic energy that's left and carried off. Okay, so what percent of the initial bullet's kinetic energy remains? Okay, so if you look in the book, you're not going to find an equation for percent kinetic energy remains. So what we do is we have to make some kind of argument here. We make an example. So I made mine in purple. Okay, so let's say initially you have the bullet moving. Okay, so here, this would be my before picture, this would be my after picture. Okay, so let's say before the collision, the bullet has 100 joules of kinetic energy. After the collision, remember it's a completely inelastic collision. Much of the kinetic energy is dissipated by kinetic friction force in drilling the hole. So it starts out with 100 joules of kinetic energy. Let's say after that I have 30 joules. Okay, what percent remains? Okay, well 30%. Okay, you start with 100, you wind up at 30, 30% remains. So how could you possibly get the number 30% out of that number and that number? Well, you took 30 divided by 100 and multiplied it by 100%. So that means you took K final, that's your 30, divided by K initial, that's your 100 joules, and multiplied by 100. So to find the percent kinetic energy remaining, you have to find the final kinetic energy, find the initial kinetic energy, divide them, multiply by 100. So here's K final. Okay, so my picture shows that they're stuck together. That's why the masses are stuck together, or written together. Okay, so K final's on the top, and K initial's on the bottom. In my original picture here, I'm using that V, a capital V, for the velocity of the combination. So I have K final on the top, K initial on the bottom, just the bullet. All right, halves go away, but I don't know what that capital V is. I don't know what that is. So now I have to conserve momentum for the collision to find that capital V. So I do P initial equals P final for the system. So I go back to my picture. Initial momentum is just the bullet. Final momentum, they're stuck together. Okay, so now I can solve this for capital V. And then this I put right there, put in for capital V. So my percent kinetic energy remaining, I have, where'd it go? I have this on the top, right there. I have M1 V0 squared on the bottom. And then for that V final, I put in that, but I had to square it. So I got my M1 squared, I got my V0 squared, and I got this thing on the bottom squared. Okay. Then I had to cancel like terms. I canceled one of those parentheses. I canceled one of the M1s. I canceled the V0 squared, and that's what I'm left with. Okay. I'm left with that ratio. So they give me the masses. Okay. I can put that in, and I find that 10.5% of the kinetic energy remains.